There is a law in our universe so fundamental, so absolute, it dictates an end not of fire or ice, but of memory. It is a verdict written into the very fabric of space-time, a decree that mandates the ultimate deletion of all information. This isn't a speculative plot from a forgotten sci-fi novel. It is a chilling conclusion drawn from one of the most rigorously tested principles in all of science, the Second Law of Thermodynamics. We see its shadow every day. A porcelain cup shatters on the floor, its intricate form dissolving into a chaotic spray of fragments. We can easily imagine the unbroken cup falling, but we never witness the shards spontaneously leaping back together to reform it. A drop of ink diffuses in water, its concentrated, ordered structure bleeding into a uniform, featureless gray. The universe, it seems, has a one-way street. It moves from order to disorder, from structure to chaos. This is the relentless march of entropy. To a physicist, information isn't just data on a hard drive, it's the very essence of specificity. It is the precise arrangement of atoms that distinguishes a star from a cloud of gas, a living cell from a slurry of organic molecules, a Shakespearean sonnet from a random string of letters. A state of low entropy, like an unbroken egg, is a state of high information. Its molecules are arranged in a very specific, complex configuration. A high entropy state, like that same egg scrambled, is information poor. The molecules could be in any one of a trillion chaotic arrangements, and it would still look like a scrambled egg. The second law states that in any closed system, the total entropy, the total disorder, can never decrease. Every star that burns, every galaxy that spins, every thought that crosses your mind contributes to this cosmic tide of rising chaos. This arrow of time, as Sir Arthur Eddington called it, is what gives our reality its sense of history and consequence. The past is the low entropy state we remember. The future is the high entropy abyss of possibilities we don't. For most of cosmic history, this was a profound but manageable concept. Information might get scrambled, diluted, and spread thin, but the core principles of quantum mechanics insisted it was never truly gone. A fundamental tenet of the quantum world is unitarity, a mathematical guarantee that if you knew the complete quantum state of a system now, you could, in principle, run the clock backwards and perfectly reconstruct its past. You could, theoretically, unscramble the egg. The information is always preserved, just hidden in the fantastically complex correlations between every particle. But then our understanding of the universe revealed a monster, a place where this comforting law of conservation seems to break down completely. It revealed the black hole. According to Einstein's theory of general relativity, a black hole is a gravitational singularity, a point of infinite density where the laws of physics as we know them cease to function, wrapped in a one-way membrane called the event horizon. Anything that crosses this boundary, light, matter, energy, can never escape. In the 1970s, the physicist John Archibald Wheeler, along with Jacob Bekenstein, distilled this terrifying simplicity into the no-hair theorem. This theorem states that once a black hole settles down, it can be described by just three properties: its mass, its electric charge, and its angular momentum. Everything else is gone. Imagine throwing a library into a black hole. The intricate data in every book, the unique chemical composition of the paper and ink, the complex history of every atom, all of it is seemingly wiped from existence, contributing only a minute increase to the black hole's mass. The universe's most complex objects are reduced to three banal numbers. The black hole acts as the ultimate information shredder.
This is not just scrambling the egg. This is incinerating the egg, the chicken, the farm, and the cookbook, leaving behind only the faintest wisp of thermal energy. This creates a paradox of cosmic proportions, a deep and irreconcilable chasm between the two pillars of modern physics. General relativity, the theory of the very large, allows, even demands, that black holes destroy information. Quantum mechanics, the theory of the very small, screams that information can never, ever be lost. For decades, this conflict has been the central crisis in theoretical physics. It suggests that our understanding of reality is not just incomplete, but fundamentally broken at its core. If information can be permanently deleted, then the past is not recoverable, the arrow of time is a lie, and the universe is capable of developing a form of irreversible cosmic amnesia. So we are left with a question that strikes at the heart of existence itself. Is the universe a perfect record keeper, as quantum mechanics insists, merely hiding its secrets in ever more complex ways? Or is it a flawed machine, destined to slowly erase its own history in the silent, crushing singularities of its black holes, marching towards a final, featureless void?
From that paradox, a chasm between Einstein's gravity and the quantum world, emerges a ghost in the machine, a whisper of radiation from the edge of oblivion that would change the debate forever. In 1974, a young Stephen Hawking, working at the University of Cambridge, performed a calculation that he initially believed to be a mistake. He was trying to unite the bizarre rules of quantum field theory with the warped space-time geometry around a black hole. What he found was that black holes are not entirely black. Due to quantum effects at the event horizon, they should glow, faintly, with a thermal energy that would come to be known as Hawking radiation. The mechanism is one of the most beautiful ideas in physics. The vacuum of space, according to quantum theory, is not empty. It is a boiling sea of virtual particles, pairs of particles and antiparticles that pop into existence for a fleeting moment before annihilating each other. At the very edge of an event horizon, it's possible for one particle of a pair to fall into the black hole while its partner escapes. The particle that falls in carries negative energy, which subtracts from the black hole's mass, while the escaping particle flies off into space as real radiation. Over unimaginable timescales, trillions upon trillions of years, far longer than the current age of the universe, this slow leak of energy causes the black hole to evaporate, eventually vanishing in a final flash of gamma rays. At first, this discovery seemed to make the information paradox even worse. Hawking's initial calculations, published in the journal Nature, showed that this radiation was perfectly thermal. It was random, chaotic, and contained no information about what had fallen into the black hole. It was like burning the library and analyzing the smoke, only to find the smoke is identical whether you burn Shakespeare or a phone book. Now, not only was the information lost inside the black hole, but the black hole itself would eventually disappear, taking any last record of that information with it into nothingness. This ignited what became known as the Black Hole Wars, a decades-long intellectual battle pitting Hawking and his belief in information loss against physicists like Gerard 't Hooft and Leonard Susskind, who argued that the principles of quantum mechanics had to be absolute. If information was lost, they contended, physics would unravel. The resolution, which Hawking himself eventually conceded in a famous 2004 announcement at a conference in Dublin, came from one of the most radical and mind-bending ideas ever conceived, the holographic principle. First proposed by 't Hooft and later given a precise string-theoretic interpretation by Susskind, the principle emerged from a peculiar observation about black hole entropy. Bekenstein had shown that the entropy of a black hole, a measure of its hidden information content, was not proportional to its volume, as one would expect, but to the surface area of its event horizon. This was a stunning clue. It's as if all the information about the three-dimensional interior of the black hole was somehow smeared out and encoded on its two-dimensional boundary. Think of a security hologram on a credit card. A two-dimensional surface contains all the information needed to produce a three-dimensional image. The holographic principle suggests that this isn't just a neat trick. It might be the fundamental operating principle of the entire universe. It proposes that the three-dimensional reality we experience is nothing more than a projection of information stored on a distant two-dimensional surface at the cosmic horizon. This idea found its most powerful mathematical footing in the ADS-CFT correspondence, a conjecture put forward by physicist Juan Maldacena in a 1997 paper that has since become one of the most cited in the history of theoretical physics.
Maldacena discovered a precise mathematical duality, a dictionary that translates the physics of a universe with gravity into the physics of a quantum field theory without gravity living on that universe's boundary. In this framework, there is no paradox. Information that falls into a black hole in the 3D bulk of spacetime is perfectly and completely described by the quantum interactions of particles on the 2D boundary. Nothing is ever lost because it was never truly inside in the first place. Its existence is guaranteed by its holographic counterpart on the surface. The Hawking radiation that eventually escapes is not random thermal noise, but a highly complex and scrambled projection of that boundary information, carrying away the story of everything that ever fell in. The implications are staggering, forcing us to fundamentally reevaluate our perception of reality. The universe doesn't delete information, it re-encodes it in a different language, on a different substrate. The cosmic amnesia we feared is replaced by a cosmic filing system of unimaginable complexity and elegance. The solid, volumetric world we inhabit may be an illusion, a grand cosmic hologram projected from a thin film of data at the edge of the cosmos. The universe doesn't forget, it projects. And we are living inside that projection, a complex, three-dimensional memory of a reality written on the very skin of spacetime.